Swayam Prabha. Digital India. Educated India.
Good day everyone, and today is the class of texture in materials, and today we will start module 2, which is basic crystallography. In this lecture we will understand crystal structure and stereographic projections. So, the concepts that will be covered in this course in this lecture are face centered cubic materials, body centered cubic material, hexagonal close packed materials, crystal structure, their Miller indices, stereographic projection and Wolf net. You see, in order to study and understand the crystallographic texture, it is very important to have the knowledge of crystal structure and therefore, the knowledge of diffraction that can be obtained from the crystal structures are important. Here we mostly deals with metals and alloys, and of course, with materials such as semiconductors and minerals and ceramics etc., but most of the time when we deal with in metallurgy is with metallic materials, and these are usually body centered cubic, face centered cubic or hexagonal close packed materials. Body centered cubic materials are basically you see iron, ferritic iron, or you can say all the steels, more ferritic steels. On the other hand, face centered cubic materials say aluminum, austenitic stainless steel, brass, copper etc. The face centered cubic materials are also divided in terms of their stacking fault energy. Yes, of course, the stacking fault energy is also present in the body centered cubic materials, but you see face centered cubic, for example, aluminum alloy they have a high stacking fault energy, copper they have a medium stacking fault energy, brass a low stacking fault energy, and therefore, their behavior differs significantly. Now, coming to the basics, you see body centered cubic material contain atoms at the corner, or you can say bases at the corners, which are made up of atoms, and on the other hand you see there is always one atom at the center, and this consists of an unit cell. In real life scenario, the body centered cubic materials unit cell may look exactly like, you see that it consists of 8 atoms at the corner of the body centered cubic unit cell, and each of these 8 atoms are they are shared between 8 different unit cells. So, these 8 atoms at the corner of the body centered cubic material are actually contributing to a 1 atom per unit cell. On the other hand, the center atom of the unit cell also contributes to 1 atom to an unit cell, making it 2 atoms per unit cell in a BCC material. Here we have demonstrated that how an atom A, which is basically the same atom as the other atom, but is shown in a different color, is shared between 8 of its unit cell, and thereby 1/8 of this atom is shared by a single unit cell can be observed. On the other hand, the face centered cubic material, as one can observe, has atoms at the corner of their unit cells. On the other hand, it has atoms at the face centered of each of its faces. So, you see that 8 atoms at the corner of the unit cell, it is shared, each of them are shared by 8 unit cell, and thereby they contribute to 1/8 of for a single unit cell. Therefore, 8 atoms each contributing 1 by 8 is equal to 1 atom contributing to a unit cell. On the other hand, the atoms which are at the faces of this unit cell, they are shared between 2 unit cell. Therefore, each atom contributes half towards the unit cell. You see, there are 1, 2, 3, 4, 5 and 6 faces in the cubic unit cell, which makes that there are 3 atoms per unit cell in the faces, plus 1 atom in the corner of the unit cell, which in real life scenario looks something like this. And therefore, there are 4 atoms in a face centered cubic unit cell, making it a very closest packed structure. On the other hand, you see hexagonal close packed material. Hexagonal close packed material is certainly different from the cubic material, which are BCC and FCC. Hexagonal close packed material are the atoms are at 60 degrees to each other, and therefore, the crystal structure basically looks like this. Few important elements, structural elements and biomedical elements and other elements are of hexagonal close packed structure. These are titanium, magnesium, and see these hexagonal close packed structures, they have, you see, 1, 2, 3, 4, 5, 6 atoms at each corner, an atom at the face center of the, this is the basal plane, and you see 3 atoms inside. So, each these 6 atom are contributing 1/6 for each unit cell, and therefore, the contribution from this 6 atom is 1, from the 6 atom below is also 1, from the face centered atom is both the atoms together contribute to 1. So, you see 1 plus 1, that is 2, and then 1 3 and then 4 5 6. So, in a hexagonal close packed unit cell there are 6 atoms in a unit cell, and one can see that both face centered cubic and the hexagonal unit cells are having the closest packed structure. So, it is important to understand these positions of the atoms in the unit cell and how the crystal structure basically looks like for FCC, BCC and HCP at least. Miller indices. So, when we understand the atomic positions of the cubic and the hexagonal unit cell, let us start with understanding the Miller indices of these unit cells. Let us start with the cubic structure, and we will only show the cubic structure, and I hope that you will go home and learn the Miller indices of the hexagonal close packed crystal, and I hope that most of the students who are doing this course may have already known the what is Miller indices and how it is found out. Now, you see here is the first image of an unit cell, and this image of an unit cell shows a cuboid, basically a cube with edges of length a, and here is the x axis, look at the pointer, and the y axis is shown here, the z axis is above, and you see that if we say that this is an unit direction. So, A is the unit direction, and therefore, if we look at this atom at the corner of that unit cell, then you see, and if we say that okay, from this origin the the Burgers vector is coming out towards this atom, then this unit is basically A. On the other hand, in the y and z direction, this direction, this x direction is not coinciding. So, you see that the Miller indices for this direction becomes A 0 0, which is A is a unit. So, it becomes 1 0 0. On the other hand, the Miller indices for the y direction, where it coincides with the y, but it is away from the x and z both, and therefore, it is not coinciding anywhere in the x and z, and therefore, it becomes 0 1 0. On the other hand, the z direction becomes 0 0 1. Now, you see, if we look at a direction which is q and its unit direction is the r vector, and therefore, you see that it goes straight and it coincides with the the corner of the unit cell here, and this corner of the unit cell basically represent that it is at a distance a from in the x direction and at a distance a in the z direction. So, the vector r is basically equivalent to a 0, because it does not coincide with the y. So, it coincides with the y at the 0. So, it becomes a 0 a, which is again this direction q is basically 1 0 1 direction. If we look at the vector p, which is coming out from the origin to this corner of the unit cell, making it as a body diagonal, then you can see that this unit vector coincides with the x direction at 1, in the y direction at 1, and in the z direction at 1, and through this path only we can reach this point, the corner of the unit cell, and therefore, the vector p basically relates to the direction 1 1 1. And one can see that if this direction is 1 1 1, then this we must know that this direction is basically perpendicular to the plane 1 1 1. And you see that we will show this one, right. If we look in the below figure, we have shown that with respect to the x axis, which we showed has a direction 1 0 0, the plane A, which is basically this plane, has the Miller indices of 1 0 0. Why? Because it is perpendicular to the direction 1 0 0. So, the plane with Miller indices 1 0 0 has the direction 1 0 0 perpendicular to it. On the other hand, if we look here, the y axis is perpendicular to the B plane, and the y axis has a directional vector 0 1 0. Therefore, the B plane has the Miller indices 0 1 0. On the other hand, similarly, the C plane, which is perpendicular to the z axis 0 0 1, has the 0 0 1 Miller indices. So, as for example, we have seen the vector q, which has a Miller indices of 1 0 1, right, and if we look into the plane, this plane, and this plane has basically a Miller indices of 1 1 0, and how it comes to be 1 1 0, one can say that if we look into this direction from the origin, like I am pointing it towards this corner, this direction is basically perpendicular to the direction of this plane, and this direction is basically 1 1 0 direction. Therefore, the plane which is perpendicular to this direction has also the 1 1 0 Miller indices. If we find out Miller indices of the directions and the planes like this, it looks very simple, but you see that let us go to the directions of the Miller indices directions, and let us show that how many, say for example, like I have shown that this p vector has a Miller indices of 1 1 1, right. Like that, there could be other vectors which are body diagonal, right, this one for example, this one for another example, this one. So, like that one can obtain body diagonal directions for the unit cell, and it could be 1 1 1 which represent the vector S, 1 1 1 bar which is another Miller indices from the family of directions 1 1 1, 1 1 bar 1, 1 bar 1 1, and then the opposite of this could also be obtained like 1 bar 1 bar 1 bar, 1 bar 1 bar 1, 1 bar 1 1 bar, 1 1 bar 1 bar, and these all 8 directions of body diagonal basically represents the family of 1 1 1 directions. On the other hand, though from the family of directions and perpendicular to it, in case of the cubic unit cell, we can find out Miller indices of the plane, but you see that it is better to find the Miller indices of the planes by using this method which is shown here. Say for example, we have the x, y and z directions with atoms present in a equal distance in both x, y and z, and say we are talking about a plane which consists of something like this, and so it is meeting the second atom in the x direction, the third atom in the y direction, and the first atom in the z direction. So, if the x, y, z intercepts are 2, 3 and 1, indices of this plane should be basically the reciprocal of this x, y and z, that is reciprocal of 2, 3 and 1, and therefore, the Miller indices of this plane is basically 3, 2, 6. So, this is basically the way in which the Miller indices of each plane is being determined. So, if we look into this plane which we said that is the 1 1 0 plane, and see if we look into this plane, it crosses the y axis at 1, the z axis also at 1, but it does not crosses the x axis anywhere, right. So, it crosses the x axis at infinity. So, you see the Miller indices of this plane will be 1 divided by infinity, comma 1 divided by 1, comma 1 divided by 1. So, the Miller indices of this plane is not 1 1 0, it is 0 1 1. On the other hand, if we look into another plane, as I said here, which is basically the plane perpendicular to this S vector, that is the x y z plane, then you see that this plane is crossing the x axis at 1, the y axis at 1 and the z axis at 1, and therefore, 1 divided by the x axis 1, 1 divided by the y axis 1, 1 divided by the z axis 1 makes it 1 1 1 plane, and therefore, we can simply understand that how Miller indices of directions and planes are determined. To let you know that the Miller indices of directions are shown by square brackets, whereas the Miller indices of plane is shown by circular brackets. On the other hand, the Miller indices of family of direction is shown by this symbol, and on the other hand the Miller indices of family of plane is shown in terms of curly brackets, something like this. Okay. So, 1 1 1 type of family of planes. Let us go to the next slide. So, here we come, as we understood the crystal structure, here we come to the stereographic projection. You see, stereographic projection is a mapping of these crystallographic planes and direction from a 3-dimensional sphere to a 2-dimensional stereographic projection, or you can say that from a 3-dimensional stereogram to a 2-dimensional stereographic projection, right. So, you see how it is done is that a unit cell, for example, is kept at the origin of the sphere, and it is kept in such a way that the origin of the unit cell is exactly at the center of the sphere as shown in this figure. And you see that the the important direction of these unit cells are the x direction, the y direction and the z directions, and these directions are basically 1 0 0, 0 1 0, 0 0 1, and it protrudes out to the circumference of the sphere, and we get poles, and these poles are basically you see 1 0 0 pole, and this pole is the 0 1 0 pole, this is the 0 0 1 pole. And imagine that this is a sphere where we are projecting. So, this is the front of the sphere, this is the back of the sphere, this is the back of the sphere, and this is the front of the sphere. And therefore, you see that in the front of the sphere, when we are projecting 1 0 0, in the back of the sphere automatically the 1 bar 0 0 is being projected at the circumference. On the other hand, if on the right of the sphere we are projecting 0 1 0, on the left of the sphere 0 1 bar 0 is already projected on the circumference. Like that, on the top 0 0 1, then below it is 0 0 1 bar. So, this 3D stereogram obtained the information of some direction of the unit cell. Like this, we can obtain information of each and every plane and direction of these cubic unit cell in this 3D stereogram. So, a stereographic projection is basically the projection or mapping of this information in this 3D stereogram on a 2D 2-dimensional plane, right. So, you see in this case you will also notice that when we are plotting this direction along the x axis, we are saying that it is the 1 0 0 direction, and it is shown by a spot, and therefore, it is called a pole. On the other hand, if we look exactly perpendicular to this 1 0 0 direction, you will get the 1 0 0 plane, and this 1 0 0 plane is basically, if we take this 1 0 0 plane and let us take the plane which is in the back side from where the origin of the crystal is matching with the center of the sphere, and you see that if we expand this plane, if we take this plane and if we expand this plane, and it expands and it reaches to the circumference of this sphere, and it will cut the circumference of a sphere and through this circumference, right. On the other hand, if we take another plane, which plane? The plane which is perpendicular to the 0 0 1, and this plane is also going through the center of the sphere, and if we expand this 1 0 1 0 plane, then it expands to the stereographic 3D stereographic sphere, and it will cut down the sphere in the circumference like this, right. On the other hand, if we take the 0 0 1 plane, the plane which is perpendicular to this 0 0 1 direction, then you see this plane, then this plane also will cut down the sphere and form, right. And this things which are forming on this 3-dimensional sphere are basically known as great circles or great circle lines. Okay. So, you see what I mean to say here, that usually in stereographic projection the directions are plotted as points or poles, whereas the planes are plotted as great circles. So, planes are also sometimes indicated by the normal to them, that is they are also represented by perpendicular direction which are perpendicular to them, right. So, sometimes they are also represented by points or poles, and they are called poles of the plane, right. So, you see here I have shown a small figure, and you can see that if there is a plane which has a great circle like this, and if its perpendicular direction is protruding like that on the circumference of the sphere, then this spot or pole is basically not only representing the direction which is perpendicular to the plane, but also the pole of the plane, right. So, on the other hand, if any plane is not passing through the center of the sphere, then for example, a plane which is the stop plane, right, the one which is having this plane is basically 0 0 1, which is producing this great circle and is perpendicular to this direction 0 0 1, but if another plane which is just above it and say this top plane which is also a 0 0 plane 0 0 1 plane, but it is not passing through the the center of the sphere, then it, if you protrude this sphere, if you expand this sphere, and it will match and it will cut the circumference of this 3D stereogram somewhere here, right, and then making it a a smaller circle. So, it is called a small circle. So, a stereographic projection is basically a true angular projection, and this true angular projection is based upon the principles of the ray of light. It shows that if a crystal is kept at the center of a sphere and a torch is lit at this point, say for example, this point is known as the point of projection, then from this point whatever shadow appears on the screen of a two-dimensional paper will make a two-dimensional stereographic projection. Okay. Let us go a little deeper and show how it is done. Say for example, we have a 3D stereogram which is like this. I hope that this is visible, and we have tried to make it as clear as possible by drawing it again. And you see that if we have a unit cell here, a similar unit cell, and you see that we have to define certain points in this 3D stereographic projection or 3D stereogram, and these points are, say, you see that B is the point of projection, A is the the point where the plane of projection lies, and so you see here is the projector screen, and A is the center of this projector screen. And as I said, if we have one great circle, say for example, we have one great circle which is north N, E which is east, south and west, and this great circle may form an important crystallographic plane. Say for example, it forms from a certain important crystallographic plane, say 100 or something, or maybe something else HKL, and therefore, this whole circle of great circle can be projected if it is torched from here, and each point of this great circle is projected, can be projected in the 3 dimension from this 3 dimensional sphere to a 2 dimensional circle like this. So, N become N dash, and the great circle goes like this, and the E which is east become E dash, and it goes like this, and the S become S dash, and then it goes, and the west which is W become W dash, and it goes like this. So, the great circle is projected on the 2 dimensional screen which is known as the stereographic projection, shows N dash, E dash, S dash, W dash with respect to the N, E, S and W of a great circle from the 3D stereogram. On the other hand, there is another great circle, right, the great circle which consists of B, E, A and W, and it goes to B again. So, if this great circle is projected on the 2D stereogram, it becomes it seems that it becomes a line, right. So, it lines where it projects the W to W dash, E to E dash, and the B and A at the same point here at A. So, you see the projection plane is basically tangential surface over the point A, which is the a point, an important point of a 3D stereogram. From this one can observe that there are each great circles could be projected either as a curve or as a line. You see another example if I give is this great circle, the great circle consisting of N A, and it goes like this to say S, and then it goes to B, and then it goes again to N, and this great circle not drawn fully could be projected as a vertical line on the 2D stereographic projection, making it the N becomes N dash, A and B becomes B, and the S becomes S dash, and you see that the great circle becomes a line. So, you see that the poles and the great circles in the 3D stereogram, which is obtained from the unit cell, which is kept at origin at the center of this 3D stereogram, can be converted into a 2D image, which is basically known as an equiangular stereographic projection, and this equiangular stereographic projection has all the informations of the crystallographic planes and directions and angular relationships between them, because they are true angular. Now, if we keep a plane at a certain angle inside this 3D stereogram, and this is shown by this red plane, and this plane basically I am talking about a crystallographic plane, HKL plane being kept inside this 3D stereogram. And if you see that a normal to the plane is protruding at the circumference of this 3D stereogram somewhere at P, and if B is the point of projection, and then the ray of light comes and spots the P, and it shadows at the position P dash on this 2D stereographic projection. And therefore, any plane, any pole on the 3D stereogram can be represented in a 2D stereographic projection. Here we have shown the same thing in a much simpler 2D manner from the side, where this is the 2D stereographic projection, and it is shown by the line because we are showing it from the side, and then you see that this is the the plane we were talking about. So, the perpendicular to the plane P is coming out from the circumference of the 3D stereogram, which is looking like a circle here, and then B, which is the point of projection, the light rays falls on this spot, and then the shadow of the spot falls on the P dash, right. The P dash is shown here in the large figure. So, this is the way a stereographic projection works. Now, you see a stereographic projection, as I said, consists of a 3D stereogram, something like that, and I said that there are longitudinal lines and latitudinal lines, and the longitudinal lines in the stereographic projections are basically comes from the top to bottom, and they are all great circles. It is given in a 3D image. So, maybe it is easier for someone to visualize and difficult for somebody. So, I will go through few slides regarding to this, and you will see that there are actually longitudinal lines, and these lines are basically great circles 3D stereogram, and if we are keeping the point of projection somewhere here, then the the ray of light will allow you to shadow these great circles and the spots on a screen, and which will look something like this. And so, this is basically the two dimensional stereographic projection that we obtain. So, in this figure what we have done is that we have given great circle, we have shown the great circle in terms of the longitudinal lines, whereas the latitudinal lines are being shown as small circle, except the one which is exactly at the center. And if you have done a little bit of geometry during your schooling, then the the equatorial line, the north pole and the south pole and the east and the west, and therefore, we can relate it to the geometrical stereographic projection that we have done to map the world on a sphere, right. But just to let you remember that stereographic projection to map the world are basically equiareal stereographic projection, and therefore, they are not equiangular. So, if you put equiangular, then it will not remain equiareal, and thereby depending upon its position, means a position of a country on the sphere and the point from where we are projecting it, a country may look bigger or smaller, and which may not be, means it will not look equivalent to the area of the country. Maybe a country with a larger area may look smaller, and a country with smaller area may look larger. And so, it is very the stereographic projection, equiareal stereographic projection that we usually do in geography is quite difficult to understand sometimes. But you see, the equiangular stereographic projection actually occur, means actually the calculation is done using the ray of light, which is quite simple. So, this stereographic projection that we are doing here is quite simple, and it follows the the ray of light. Now, you see that the latitudinal lines, except the equatorial line, this equatorial line, see I have started showing it on the 2D stereographic projection, because it is much easier to observe it on the 2D instead of the 3D, which is here. This equatorial line is basically the great circle. All the other latitudinal lines shows the small circles, right. On the other hand, all the longitudinal lines shows the great circle. You see, all the longitudinal lines shows the great circle, and this kind of projection of longitudinal lines and latitudinal lines are basically known as Wolf net or meridional stereographic net, and these are used to understand or calculate angular relationship in the stereographic projection. Here is another view of the stereographic projection from the the direction of the point of projection, and one can see that this stereographic projection, how nicely it divides the angular areas into from the top to bottom into longitudinal and latitudinal lines. So, this is from this is drawn by my student Jugal Kishore Banikke, and so basically you see a wolf net, which is basically a ruler to observe and quantify the stereographic projection, is shown. The orange colored wolf net has basically a degree graduation of 2 degree, and the blue colored wolf net has a graduation of 10 degrees. So, one can map the angles between planes and directions and everything with respect to this wolf net, and you see, as I said earlier in the slide, that longitudinal lines, that is these lines are always great circle, whereas latitudinal lines except the equator are always small circles. So, you see, when say for example, two planes are present in a crystal and we need to measure the angle between these two planes. Now, you see if we project this the brown color plane, it will project out to the circumference of the 3D stereogram like this and it will form a great circle. On the other hand, if we take this blue colored plane and it will protrude outside to the circumference and become another great circle, and this will happen only if both the planes are passing through the origin. And therefore, you see that if we need to find out the angle between these two planes, we have to see that both the planes has to pass through the center of the 3D stereogram. And if we draw a perpendicular to the brown color plane and it will protrude and come out at P 2, and if we draw another perpendicular direction to the blue colored plane, it will protrude to another direction, say P 1. So, we obtain P 1 and P 2, two positions on the circumference of the 3D stereogram. Now, if both of these planes are passing through the center of the sphere, and then if we connect P 1 and P 2 and if we expand this over the circumference of the sphere, it will form another great circle. And because it forms another great circle, then if we the angle between P 1 and P 2 could be obtained from the angular deviation, because this 3D stereogram has an equiangular division, right. So, the angle between the two planes alpha can be obtained from the 3D stereogram from the angle between two direction P 1 and P 2. But you see that in the 3D how difficult it becomes to find out the angle between P 1 and P 2. But if we have a 2D stereographic projection from this 3D stereogram and if we could superimpose the Wolf net over it, you see like this, we can utilize this Wolf net to find the angular deviation between the two planes, right. Say for example, if you have two planes which are something like this, then we can find out the angular deviation between the two planes, which is by calculating, you see as I said that the larger ones have a 10 degree graduation. So, you see 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120. So, the angle between the two planes can be obtained from the Wolf net to be 120. But to let you know this, that we can obtain the angle between the two planes only if we can superimpose their poles over the great circle. If the poles are superimposed on the small circle, then the angle measurement may not be correct, and therefore, you see when we obtain this Wolf net and we showed angle between various planes, like for example, planes C and D, and we have always tried to superimpose the poles of these planes on a single great circle, so that we can measure the angle correctly. For example, the angle between C and D, which is being superimposed on a single great circle, this one, and is 10, 20, 30 and 40. The angle between two planes E and F, or two planes whose perpendicular directions are E and F, or the poles are E and F, are again 10, 20 and 30. And you see that here also we have superimposed the two planes on the great circle. Therefore, in order to measure the angle between two planes, we have to keep the poles of the two planes on the great circle of the 2D stereographic projection. Moreover, you see that we can also observe that how the angle or the positions of the poles of different planes may vary if the stereographic projection is rotated. You see that let us rotate the north and the south poles, N and the S poles, and you see we should try to imagine that this is like a circle, right, like a sphere, right, projected on a 2D plane, and therefore, it becomes a circle, right. So, if we rotate this stereographic projection on the north and the south plane, thinking that it is a sphere, then what will happen? If there are two planes A 1 and B 1, and if I am saying that I am rotating these two planes along the n s direction by 60 degrees. So, A 1 goes to A 2, and therefore, you see we have to go 10, 20, 30, 40, 50 and 60. So, A 1 goes to A 2, and therefore, the rotation is 60 degrees. Now, the B 1, which is with respect to the A 1, is present here, and I have shown it by the plus sign, because the poles are protruding outside, right. Now, if you see that if with respect to A 1, the B 1 is rotated. So, the B 1 will rotate 10 degree, 20 degree, 30 degree, 40 degree, and then when it will rotate and it will come out here in the opposite direction 50 degree and 60 degree. So, the position of B 1 now changed from here to here, right, because now we are seeing the opposite direction of the sphere. On the other hand, if we could protrude the opposite pole of B 2, it will be protruded directly here, exactly opposite of it, because it will pass through the center of the sphere and will protrude out somewhere here. So, I have shown it by the minus sign. So, in this lecture, we found out that the knowledge of crystal structure and diffraction is essential to study and understand the crystallographic texture. The crystallographic planes and directions could be mapped into a 2D or the 2-dimensional plane using the method stereographic projection. Wolf-Net is a projection of the sphere ruled by parallel longitudinal and latitudinal lines on a 2-dimensional plane. Angular relationship between crystallographic planes and directions actually could be easily determined using stereographic projection and Wolf-Net. Thank you.